Here we're going to work on homework 4, exercise 13, this one about the birthday paradox. Here we're going to compute how many people need to be in a room so that the probability that 2 people have the same birthday is greater than or equal to p. And we're going to assume that there are 365 days in a year. I guess we're also assuming that people are equally likely to be born on any of them. Okay, so the first thing that we're going to do is we're going to guess about how many people need to be in a room in order for there to be a 50% chance that 2 of them have the same birthday. And a pretty common guess is 182 or thereabout, 183, something like this, because that's the probability that, like, if you go into the room, that someone will share your birthday, or roughly like that. But it turns out what's fun about this problem is the answer ends up being a lot smaller than 182. Okay. So we're going to write a bunch of R code, and we're going to run a bunch of R code. But first, we're going to try and strategize what kind of R code we're going to write. The first thing that we're asked to do is create this function called birthday collision, which takes in a positive integer n and returns the probability that in a room of n people, we can find 2 people who share a birthday. Okay, and then it asks print both birthday collision 2 and birthday collision 365. I really wish I had written 366, but it's really the same idea. Birthday collision 2 should be 1 in 365, right? Choose which birthday whoever comes into the room first, choose their birthday, and then it's just the probability that the second person in the room has that matching birthday. And birthday collision 366 or 365 will be very close, if there's 366 people in the room, there's only 365 days to choose from. So necessarily 2 people have to be born on the same day. Okay. So how do we compute this birthday collision? We want to know what's the probability. What's the probability that that in a room of n people, two or more people share the same birthday. There is a shared birthday. Okay, and actually how I want to think about this is I want to flip the question. Oftentimes this is a good technique in probability, is that we're going to instead do 1 minus the opposite so that no 2 people share the same birthday. Okay, this is, again, implicitly in that room of n people. Okay, and how do we figure out this? I think I'm arguing this is an easier thing to figure out. Okay, well, let's think about some different cases. So when n equals 1, then no 2 people are in the room. A birthday. Okay, if n equals 2, then we're going to think about it. There's sort of one person in the room who has some birthday, and the second person is going to come in the room, and there's a 1 in 365 chance that they share the same birthday. So there's 364 out of 365 birthdays that will not share collision. So chance of no shared birthday. For n equals 3, well, first what we need to happen for n equals 3 to work, the third person walks into the room, is first we need for 2 people, the 2 people that are in the room to not share a birthday. And then what do we need? Well, we need that the third person who comes in the room has one of those remaining 363 birthdays. Okay. And in fact, this kind of implies something here. So maybe I'm going to change this to, maybe I'm just going to change this to what I had written up here. Oops, delete that, delete this. Which is the chance that of no shared birthday. sort of, you can see that actually we can extend the pattern out. There's a 100% chance of no shared birthday here. 365 or 365. So that's just multiplying by 1, and same deal here. Okay. So for general n, what is it going to be? Sort of on the top, it's going to be 365 times 364 times all of the way down to 365 minus n plus 1. Remember that plus 1's important, because when n equals 1, it should be 365 as sort of the last number on top. And we're going to divide each of these things then by 365. Okay, so the answer to our question in probability, remember, is 1 minus this thing. I think I accidentally copied the question 2 there, though, so let me try this again. Gotta fix this bug in this program. Okay, sorry, this is a little annoying, but so what's the probability of what we're looking for is that that two or more people share a birthday. Is going to be equal to 1 minus this general n case. All right, so the next step here is that we're just going to implement this in code. And of course, this is for an n-person room. Open a new file. We're going to do part B. What does problem B ask for? It asks for a function birthday collision, which is a function which takes some n. This is our number of people. And it's going to return the probability that 2 of them share the same birthday. Before we do this, though, I kind of want to play around a little bit. I want to do 365 down to 365 minus, I don't know, 10 plus 1. Make sure we get that list of length 10. See, I didn't get that here. We want to do this actually instead. Okay, so that was good that I checked. And then we can, if we want to, we can divide each of these by 365. Okay, and then we can multiply these together. I think the command is prod for product. Okay, so this would be the case for 10, 1 minus this product. But of course, now 10 is going to be n. So here's our probability of birthday collision. And we can check birthday collision 1. Better give us that there's no birthday collision. And 2 should give us something that's 1 over 365. So let's check, and indeed it equals 100 over 365. And then lastly, 366, or because of rounding error, it's going to be the same. Definitely there will be a birthday collision if every birthday is represented. This is kind of the more correct thing to have written. Okay, great. So let's capture these, print those out. Now we're going to write a function called birthday paradox. Sorry, this is going to be our function, and it's going to take some value of p. And what's it going to do? It's going to kind of loop through these values of n until we find something that birthday collision is greater than or equal to p. So I'm going to have, let's have n start off as 1 in case p is 0. And then it's going to be while birthday collision of n is less than p. What are we going to do? All we're going to do is increment n. Easy. And then we're going to return n. Okay, so let's run this guy, and let's check. What if I say birthday paradox of 0.5? I get 23 out. Okay, so that says that in order for, if we have 23 people in a room, then they're going to have a greater than 50% chance of having the same birthday. So let's check that with our other code. So birthday collision 23 better be bigger than 0.5, and it is. And birthday collision of 22 better be less than 0.5, and it also is. Okay, so that's a 0.5. For 0.25, I don't remember the answer, so I'm going to guess. I think for a quarter chance that two are in the same room, at like 18. Let's find out. 15. For a 0.75 chance, maybe 30. 32. And my guess for this last one for 0.99, I actually don't think it's that much bigger than 32. It's probably like 45 or something like that. 57. Okay. So I made some guesses. I was wrong on every one of the guesses, but it helps, it helped me to kind of calibrate, guess what I was going to see before I hit enter to experience it.